Now let's continue with our lesson. And we have another example for Fourier transform, which asks us the Fourier transform of a rectangular function. And let me write the question itself. Now, this is our question. So how are we going to find the Fourier transform of this rectangular function which is shown in the graph? So our first step is to find the derivative of this function, which is, let me write here, we have d over dt, the signal x in t, and then we have t here, and then in this part, as we see, the slope is plus infinity. This here, the slope is minus infinity, and we will show them in this graph in terms of their delta functions. And here we have the amplitude is a. Here we have the amplitude is a as well. So since it is plus in this part, in minus tau over 2, we will gonna show it like this. It is the amplitude here is a, and here similarly it is tau over 2, and the amplitude here is a, and then the rest will be just 0, because here in all of this section the slope is 0, and all of this section the slope is 0 as well. So what we let me show it in blue to have a better understanding, better visuals. And here is our graph. And in order to obtain the Fourier transform, we will just write d over dt xt is equal to, we have the amplitude a times delta t plus tau over 2 minus a times delta t minus tau over 2. Okay, because why we multiplied with a is because delta normally has an amplitude of 1, but we need amplitude of a. That is why, that is the reason why we multiplied with a. And here, since it is minus t tau over 2, it is the reason why we have an plus here. And here we have minus for obvious reasons, as this is minus amplitude. And that's it. And as we continue, we compute the Fourier transform of both sides. And what do we do here is j omega times x omega equals to, here we have the we could just take the coefficient outside and take into parentheses. And what do we do here is the Fourier transform of delta function is 1 times, since we have shifted it by this amount, we will just multiply it with j omega tau over 2. And here we do the same thing, minus j omega tau over 2. And here we are done. We just wanted this section over here, so we will divide it both sides to this expression j omega. So what do we do? What do we have as a result is, let me copy this section, copy and paste, and we just have the same thing divided by omega. Let me just write it like this, omega here and j here, and these two expressions are multiplied. Let's assume that it's just a trick to show you something. If I multiply it by 2 and divide it by 2, the expression won't change, as we know, but we can express this value over here as a simplified version, which is sine omega tau over 2. This is the reason why the other equation, and we can just show it like that, and eventually we will have let me show it like this. Wait. Yes, now eventually we will have, sorry, this expression over here, a over omega sine omega tau over 2 times 2, right? Yeah, 2. And we just want to show it in a simpler form. That's why we want to multiply it with, and let me show it in blue so that we can understand the difference. We'll multiply it with omega tau over 2, and then we also want to divide it omega times tau over 2, and this one can be shown as sample omega tau over 2, right? This expression over here. It's a new way of showing it. And we have omega here, they will cancel out, 2 here, they will cancel out, and eventually we will have our Fourier transform as a times tau times sample omega tau over 2. And this is our result, and this is eventually the Fourier transform of rectangular pulse. Fourier transform of a rectangular pulse. Okay, and that's it. Here is our result. Now let's move on to another question. Let me write here example, and it says it has given us another graph, and it wants the Fourier transform of that graph. So this is the graph that we are asked the Fourier transform of. And what do we do here? We need to split this graph, because we cannot just simply, as we did in the previous example, like draw the impulses and etc. No, it does not work like this, because these two are actually a addition of two other graphs, which are, let me write this here. This is, let me say, graph, and this graph is addition of two, which are one of this one plus one of this one, which is, here we have minus 2, 2, and we have 3 here, we have minus 5, 5, and 4 here. And we actually need to find the Fourier transform of these ones individually and then sum them up, as we know that Fourier transform has linearity property, and then if we sum the signals itself, we need to sum the Fourier transforms as well. So what do we do here? We just apply the previously found formula, and we know that we have amplitude times tau. Like, this is tau minus 2, and this is tau, and this is the amplitude. So we basically first need to find the area times the sample omega tau over 2. So what do we do? Area is, here we have 10, here we have 4, and the area is 10 times sample omega tau over 2. What is tau over 2? Tau over 2 is this part, so it is just 5. And then we do similarly the area here. We have 4 here, 3 here, the area is 12 times sample. The tau over 2 will give us 2, so omega times 2. Alright, so eventually we can rewrite these ones. Sample means the sinus inside expression over the same expression. So let me rewrite it like this: sine 5 double omega over 5 omega plus 12 times sine 2 omega over 2 omega. This is our final result. Alright, now let's move on to another example. And let me just rewrite it. Okay, so in this example, we are said that we have an xt signal, time domains x signal, which is rectangle t minus 1 over 2, where rectangle itself is given, rectangle function is given. So the rectangle function is given as it is 1 as when t is for t between minus 1 over 2 until 1 over 2, and it gets 0 otherwise. So let me just write the rectangle function as it is written here. Until from -1/2, 1, -1/2, -1/2, 1, 1. Okay. Here we have the rectangular function like this. Okay. And then what do we do? And this here, the signal is shifted by 1/2. So we have a time shift here. And eventually we have our signal like this. 1. Okay. So our signal y, let's say y equals to all this, is equal to this sum of this portion and then the time reversed portion. And then let me write how the time reversed portion is. It's just the opposite as we can see here. This is, and when we add these two up, as it is shown here, when we add these two up, we have a function which is a rectangular function which is bigger than the first one. And we have something like this. 1, -1, 1, and we have our function y. And that's it. And then here we are asked for the Fourier transform of this. As we know, the Fourier transform is found by calculating the area times sample times, let me write it here. The Fourier transform is the area. Here we have 2, here we have 1, and 2 times sample omega times omega over 2, which is 1. And here is our answer. But in the question, as we can see, we are given another information which we can make use of it. This is basically equal to 2 times sine omega over omega, as we knew. And we need to know another piece of information here in order to continue to make other equalities. So this one equals to 2 sine theta cosine theta, as we know. And if we just do it sine theta, it will equal to 2 times sine theta over 2 times cosine theta over 2. And then we can just write this as similarly here. This one equals to 2 times, we have the omega here, times, instead of sine omega, we will just use this equality and write 2 sine omega over 2 cosine omega over 2. And that's it. We can play with it, also have other equalities, but this is the main point which I wanted to illustrate you. And then now let's move on to the next example. So our examples tells us that we have a signal value x in time domain, and it is equal to unit step functions t minus 2 times unit step function t plus 2. And we are asked its Fourier transform. So what do we do here? First, let me show the graphs itself. Ut minus 2 will be a graph like this. We have 1, we have 2, here we have 0, and then it gets to value 1 when it reaches 2. And we have the other function, which is something similar, but like this. ut plus 2. We have t here. And then if we were to multiply these two, what did we have? And we will observe that one of them, let me just try to multiply both of the values, and then this is our first function, and then this is our second function. Here, since the 0, it takes 0 values, the resulting function will have 0 as well. And so the resulting function will, let me illustrate it like this. We will have 0, 0 until this point, and then we will have 1 afterwards. So we will find the Fourier transform of this function eventually. And then how we will do that, this is our new function. Let me call it y. No, sorry, it's x. And then what did we do in these situations? Here is 2, here's 1. Our first step was to find the derivative function, and then here we have the derivative function xt, and then here we have a t, and here we're going to plot the slope, and then this portion's slope is 0, this portion's slope is 0, this portion's slope is plus infinity. However, we need to like show it with a delta function, which amplitude is 1, as this here is the amplitude is 1. So let me just show it like this. And this is our function. And however, is it done? If we were going to continue with our calculations, it's not done, because we are going to calculate also the DC value. Let me show you how. d over dt xt, as we calculated it, it was delta t minus 2, and then we find the Fourier transform of both sides, which is j times omega times the Fourier transform omega times equal to the Fourier transform of delta is 1 times. Here we have the time shift, so we just multiplied with minus j omega 2, and then we find the Fourier transform. However, we are not done, because we need to find the DC value. Like, you might be confused why we didn't find the DC value in this type of rectangular functions, but we are going to find the DC value when the function is like this. The reason why here, we have a limited portion which are non-zero. This portion has a value which is non-zero. However, here is not limited portion. It goes until infinity. So in these graphs, we need to find a DC value, whereas in these ones, we are not required to, as a DC value will give us 0. So having said that, let's continue our solution, and we are just going to calculate the DC value. And then the DC value, it's just the average of the graph. And we take 1 plus 0 over 2, which gives us 1 over 2. And let's take the Fourier transform of this. We remember how to find the Fourier transform. We just take the value itself and then multiply it by 2 pi and then multiply it with delta omega. This is also shown, the proof of it is shown in a previous video if you're interested to watch it. And then we just add this result to our function Fourier transform, and our final result will be this expression over here plus pi times delta omega. And this is the result of our example. Now let's continue with our examples. This time our example asks us to find the Fourier transform of the step signal, which is just this, right? Let me show it. Which is just this. And it seems pretty basic and easy. However, it's not as it seems. me show you the reason. So we could just use the formula as we can think, but the Fourier transform formula has one condition. That is, the function itself should be absolutely integrable. So is it integrable? Let us see. Is it integrable? Absolutely integrable. This value, is it absolutely integrable? The function itself is equal to its absolute value, as there's no negatives. So if we were trying to integrate all the area underneath, we would see that it gives us infinity. So however, our condition was if it was less than infinity, we could use the formula. However, as it is equal to infinity, we cannot use the formula. We can't use Fourier transform formula. So we will use a little help from the Sygnum function. The Fourier transform of the Sygnum function is is 2 over j omega. Or Fourier transform of the Sygnum function is this one. And the Sygnum function is a function which is it has -1 until the value 0, and it takes the value 1 afterwards. So Sygnum t, and then in order to find the Fourier transform of the unit step function, we need to apply some steps. First step will be the amplitude shift. Well, and then after doing the amplitude shift by 1, we will notice that our function will be something like this. Oops. This is 1 plus Sygnum function, which is the twice of the step function. Okay, let me write it 2, and then we have 0, and then we have t, etc. And then as we have found out that ut is actually 1 plus Sygnum function over 2, right? We can just write it by splitting the fraction, and then here we have our final result. And then we need to take the Fourier transform of both sides. Fourier transform ut equals to Fourier transform of 1 over 2 plus 1 over 2 times Fourier transform Sygnum function t. And then as we know here, the Fourier transform of 1 over 2 is 1 over 2 times 2 pi times the delta function omega plus 1 over 2 times Sygnum function's Fourier transform was 2 over j omega. And then here we have the Fourier transform x omega. And here we just need to simplify these ones. And here we eventually have our results, and then pi times delta omega plus 1 over j omega. Here we have concluded our example, and this is the Fourier transform of a unit function. Now let's move on to the next formula. And here we have an example. Sorry, I said formula, but I meant example. And here we are given a signal, xt equals u2t, and then we are asked for its Fourier transform. So how do we compute this? First of all, we are not required to jump and do the rules, the amplitude shift, and etc. Why? Because our time step function is like this, right? We have 1, we have 0, and we have t. And then if we were going to plot u2t function, what we would observe is that when t changes, it takes the same values that it previously took. What I mean here is these are the same. As when t is 1, it will have the value 1. Here, when t is 1, we will compute u2, which would give the value 1. So eventually what I'm trying to say is these two functions are eventually the same. So that's why the Fourier transforms are also the same. So we are not going to say, okay, we have amplitude shifting, so the Fourier transform will be we won't apply the formula that we were discussing previously in the graphs, etc. So the Fourier transform eventually of this is the same as the unit step function as we calculated it. So the final result will be this one again. Now let's calculate the Fourier transform of impulse signal. So first step is to check if it is absolutely integrable, and as we know, the impulse signal area is 1, so it is absolutely integrable. Yeah, it is not. It is less than infinity. So we are going to apply the formula. And then instead of here, we will write delta function. And as we know, we can write it as like this. And then we are just going to replace t by 0, and as it will only take a non-zero value at 0. And let me show it like this. E to the power of 0 will get 1 dt, and eventually we will have 1. And this is the end of this example. Now, let's move on to the next example. We will calculate the Fourier transform of we have the Fourier transform as shown. We have the Fourier transform this time. We are asked the signal itself. 2 cosine omega sine 2 omega over omega. And we are asked to find the function when it takes the value 0. And how do we do that? We are asked to go reverse direction this time. How do we do that? Now we are given the Fourier transform. Let me write this again. Sine 2 omega over omega. And we know let me remind you of a trigonometric function equality, which is 2 times cosine A times sine B equals sine A plus B minus sine A minus A this time. All right, this is important. Let me show it like this. And we will replace this as sine 3 omega minus sine minus omega. We would need to write over omega equals 2. I will just write sine omega plus here, as sine is an odd function. And then we can just split these up, sine 3 omega over omega plus sine omega over omega. And then we can multiply it with 3 and divide it to 3. And then what do we have here? We have this part over here will be sample 3 omega, and here we have will be sample omega, and then we have 3 sample 3 omega and plus sample omega. This is the Fourier transform. And then here we know how to write the function itself, as we know that the signal can be found as reverse direction. For example, here this one will be found as tau over 2 is 3, so here we have 3, here we have minus 3, and then we know also the amplitude as the area will give us this coefficient. So here we have 6. In order to have 3 as an area, we need to have 1 over 2 as an amplitude, and this is, let me write it as h1t, and t, and this value over here will be, we have tau over 2 as it is 1, let me write this minus 1, and the area is 1 as well as the coefficient is 1. So since we have 2, we will have an amplitude of 1 over 2 here as well, h2t. And then when we add these two up, we will have our function. So we are asked to find h0, which is equal to, when we have h0 here, our value is 1 over 2. When we have 0 here, we have 1 over 2 as well. So our function, our results will be 1. And this is our final result. Thank you for listening to me. See you in the next lecture.